recently updated and it got so much worse. It was like forcibly updated. It didn't get me choose.
Yeah.
I did not want that.
It's like forcibly upgrading your eating habits. It's no fun. Alright, let's go ahead and go to page 202. Let's do some examples, start playing through some examples here for limits. So on the page 202, numbers 1 through 6, you have matching. So you're going to look at the graphs and then you're going to match using horizontal asymptotes as an aid for that. Now remember, the horizontal asymptote is defined as the limit goes to infinity, it goes to that value. So if you look at, for example, A, let's just take a look at A, and you could take a look at 1, and let's look at the graph A. Graph A has, it's kind of like isn't there like, you can cumbersome text like isn't, you know, like before emojis, people put smiley faces with like parentheses. Isn't there one where they have like a,
Yeah, where it's like shrugging, like
yeah, shrugging. That's what it looks like on A there, right? So it's the shrug guy or something. It's not actually accurate. Come up, come down. Okay, kind of. But the horizontal asymptote there, you can see, is at 2, right? So it goes out at 2. Is that right? So yeah, the horizontal asymptote is at 2. So the limit as x goes to infinity is 2. So you would go down to the graphs or the equations 1, 2, 3, 4, 5, and 6 and try to figure out which one goes to 2. Now we haven't spent, well, I think we did these last year, but you would look at, like we could start looking at number 1. That one has 2x squared over x squared plus 2, so that might cue us into possibly one that would have a horizontal asymptote at 2, possibly, and then possibly number 2, and then possibly, I guess a lot of them have 2 involved, like the 2x squared, so on and so forth. So let's take a look. I guess other things you could do. Let's take a look at number 1 though, and it says f of x is equal to 2x squared over x squared plus 2. Now we briefly discussed this. When we go to take the limit as x approaches infinity and negative infinity, you would look at the largest value of x in the denominator in terms of like the largest, not value, but the largest exponent, so x squared, and then you would divide everything by that. So there's only x squared, so we're going to divide everything by x squared, so 2x squared over x squared over x squared over x squared plus 2 over x squared. And we talked about that last time, where you're actually multiplying top and bottom by 1 over x squared, 1 over x squared, which is just multiplying it by 1. And what we do that for is because the driving force in taking limits as they go to infinity is, a basic example is when you divide by a variable, 1 divided by infinity, that goes to 0. Or even like I think we talked about last time, you can have a large number divided by x. Yeah, this looks large to us, but then when you divide it by infinity, it's still 0. So the driving force is whatever is the largest exponent, because you could have, you know, x to the 10th, you're like, man, that's really big. However, if it's over x to the 11th, then that is going to simplify out to be 1 over x, and then it's still going to go to 0. So the denominator is what drives it. So in this case, when we look at this one, we would say, okay, this is number 1, and we're trying to find a graph that matches that. We look at number 1, okay, this cancels, and so you're left with 2 over 1 plus 2 over x squared, right? And this is the limit as x goes to infinity. So in this case, the limit as x goes to infinity, 2 is a constant, so it stays, 1 is a constant, so it stays, and then 2 over x squared, right, would go to, we would take the limit of that, 2 over infinity, that just goes to
Goes to 0.
0. And so the limit as x goes to infinity would be 2 over 1, right? Which would just be 2. Now we look at, like we say, okay, that matches A because the limit is 2. Now as x goes to negative infinity, you still would apply the same rule here. We just plug in like negative infinity right there. Does the same answer occur where you plug in a negative infinity? Sure, 2 divided by a negative infinity is still 0. So you still get 2 over 1. So it's still 2. So yeah, so far 1 could match to, I think this was letter A, right?
Yeah.
But if you look at other graphs in there, well, let's take a look at B. Does B have a limit going to 2? I mean, you have it in the book. I'll put it up here just for viewing purposes and showing, but like this, right, comes down.
Oh, number 2, the equation.
I'm sorry, B. Does that look like it's going to a limit of 2? You know, 2 is up there, negative 2 is down here.
Oh, yeah.
You know, does it look like it's going to a limit of 2? I mean, does this go to 2 though?
The end. It doesn't actually reach 2.
No, it doesn't. It just shows it going down to like the origin, right? It doesn't like extend out. If you look at C, squeeze C in here, does C look like it's going to 2?
Yeah.
Well, 2 and negative 2, right? So C comes up like this, right? So it's got a horizontal asymptote at negative 2, asymptote at negative 2, and at 2. So 2 and negative 2, right? So what we, like for equation 1 says yes, it's got a limit, horizontal asymptote of 2 because the limit goes to 2. So far, this is just 2 and negative 2, so it's not going to be C. This one, the graph doesn't go to 2, and it actually shows it kind of going down a little bit and up a little bit, so it would be going towards both possibly, so it's not going to be B. So then you look at the other D, what does D go to? D almost looks like it's got a horizontal asymptote at where?
Like at 0?
Yeah, possibly at 0, right? It looks like it's, so D is going to be out. And then that leaves us with E. E spikes up and then comes down and then goes up like this. And that's at 2. So E is a possibility, right? So A is a possibility, E is a possibility, and then Mike all over F. I wasn't going to plan on doing all of these, but it's a good discussion to have. F also is at 2, right?
Yeah.
So the only ones that might work for us are F is a possibility, E is a possibility, and A was a possibility, right? So all the other ones are not possibilities. So then with just looking at using horizontal asymptotes as an aid, we've analyzed, okay, we have A, F, and E. Obviously you could just plug this into your calculator, see what the graph looks like. That's not the point. The point is try to match without graphing it. So if we take a look at this, is there anything else about this? We've already analyzed the horizontal asymptote, so outside of horizontal asymptote, is there anything else about equation 1 that would help us look at, is it going to be E, A, or F? There's something specific I'm looking at without graphing it, but something algebraic. Are there any domain restrictions on this one? Domain, denominator, any domain restrictions? Are we gonna get out a -2 with something being squared? No, so no domain restrictions, but was there any domain restrictions on any of these? Do we see any like vertical asymptotes where it can't cross on any of those? The answer is no, right? Those all. So then the other thing you can look at is, can we find out where it crosses the, does this one ever cross the x-axis for this equation? And we want to figure out where it crosses the x-axis, right? Wherever a graph crosses the x-axis, what's your y value? Your y value would be 0. In order to make the y value 0, you would need your numerator to be 0. So where does that equal 0? At 0, right? So at x equals 0, so not here, but at x equals 0, we are going to have a x-intercept. Oh, I'm sorry, a y-intercept. I'm sorry, an x and a y-intercept actually, but whatever, if x is 0, it's a y-intercept that I'm finding. So in this case, so if x is 0, I'm finding the y-intercept, which also happens to be where your x-intercept is occurring. So in this case, does this have any x-intercepts? No. Does E have any x-intercepts? Nope. And so then making sure my graphs are correct. So what's the only one it's going to be then? F. So we analyze it that way. So F would be what we aim for. Okay. So that's how you do some of those. If we take a look at number 7 and 8, 9, 10, 11, 12, those ones. On those ones, it says use a graphing utility to complete the table, estimate the limit as x approaches infinity, then use a graphing utility to graph the function, estimate the limit graphically. So all you're doing is plugging in large values for x and seeing what happens. On that, they have you plug in 10 to the 0, which is 1, right? And then plug in 1, then 10, then 100, then 1,000. You don't need to plug in all those values, just plug in a couple values or just one value and see like a large value, 10 to the x. But we understand that you plug in a small value and they can watch the trend from small to big. Where is it going towards? So you don't need to do a bunch of work on those tables. You don't need to fill all those tables in. Graphically, you can graph something and look at what it goes to. May have to zoom out a little bit, right, to see what it does as you get large values of x potentially. So that's all you would do on 7 through 11 there. For 13 and 14, they say in exercise 13 and 14, find the limit of h of x if possible. And what they have there is h of x is equal to f of x over x squared, or h of x is equal to f of x over x. So if we look at 14, so you guys have to do 13. If we look at number 14, 14 states for us f of x is equal to, number 14, f of x is equal to negative 4x squared plus 2x minus 5. Okay, and then for part A, they say h of x is equal to f of x over x. And they want you to find the limit as x approaches infinity of h of x. So so really you're just finding the limit of f of x over x for part A, and f of x is negative 4x squared plus 2x minus 5 all over x. So you're just finding the limit as x approaches infinity of that fraction right there. In this case, you can do the algebraic method of look at the largest exponent in the denominator and then divide everything by that. So everything's divisible by, in this case, we divide everything just by x. And so if you would get negative 4x plus 2 minus 5 over x all over 1. Not showing the step, but just taking everything divisible by x, by x, by x, and by x. And then when you do that and you take the limit, you would recognize that you end up with negative 5 over x is going to go to 0, the constant of 1 in the bottom, and then you would really say, oh wow, I get negative 4x, where x is going to infinity, so this number is going to be negatively infinite, right? Gigantic. So this, you're ending up going to negative infinity. So would we consider there to be a limit for this one? If it goes to negative infinity, is there a limit that it goes to? Does it stop at?
No.
No, so it does not exist. So then for part B, they have f of x over x squared. Part B is f of x over x squared, and so we say, okay, the limit as x approaches infinity of negative 4x squared plus 2x minus 5 all over x squared, and you look at the driver in the denominator, which is the x squared. So you get negative 4 plus 2 over x minus 5 over x squared all over 1. And then you would take the limit as x goes to infinity, and you recognize 2 over x goes to 0, 5 over x squared goes to 0, and you're just left with negative 4 over 1, which is just negative 4. So the limit would be negative 4. And we don't need to do part C. I think that's fine. Okay, then we jump up to like 16 and 18. Let's take a look at 18 because it's got rational exponents, 5x to the 3 halves, and some ones like that. So let's take a look at 18b. And b is 5x to the Hey!
Do you have Caleb this summer?
Caleb.
Caleb, no, I must be an hour ahead.
For geometry?
Yes.
Geometry's next, Caleb.
Okay.
Caleb Bell?
No, Anderson.
I do. Yeah, he may be gone.
He will be gone. I just am an hour ahead. I went to the
Okay.
Sorry.
No problem. X goes to infinity of 5x to the 3 halves over 4x to the 3 halves plus 1. So, when you see this, you can start to recognize that like a plus 1 as x goes to infinity is going to become inconsequential. So like the addition of 1, or even if you had a plus 1 up top, or even if it was plus 1,000 or 10,000, that value as x goes to infinity If this is becoming exponentially large, this is just, it becomes inconsequential. So, you can divide everything by x to the 3/2, which is fine. Also mentally recognizing 1 divided by x, even if it's x to the 3/2 or whatever, is just going to be 0. That becomes inconsequential. So, and then you recognize like, oh, these two values are the same. So really what it's going towards is 5/4.
Yeah.
But you can also show, dividing everything by x to the 3/2, this divided by x to the 3/2 gives you 5, this divided by x to the 3/2 gives you 4, this divided by x to the 3/2 taken to infinity, that just goes to 0. So 5/4 is all you're going to get there. Okay, let's go and look at number, these ones are kind of all the same-ish. Let's take a look at 28. Because 28 includes a radical with a binomial. As x approaches negative infinity on 28, negative infinity of x over square root of x squared plus 1.
Does the square root really change anything? Would it just?
Well, since it's just the, so you can't, I don't have one, well, like this one, we didn't show the step, but it was like 1 over x squared over 1 over x squared, right? And then that went into everything. The problem is if you say, okay, 1 over x squared, right, 1 over x squared, is that 1 over x squared can't come underneath the radical,
Yeah.
right? However, what can come underneath the radical is 1 over the square root of x squared, 1 over the square root of x squared. So if we take 1 over the square root of x squared into the top, what's the square root of x squared?
X.
That's just going to be x, right?
Yeah.
But then we take square root of x squared plus 1 over x, it is, I guess I'll show this, divided by the square root of x squared, like that. On the top, x over square root of x squared is just x, so that just goes to 1 over, and then with the square root and the square root, right, you can combine that into just 1 square root, right? And then that x squared can go into both, and so x squared into x squared would just be 1 plus 1 over x squared. That x squared goes into here and into there. It's still the radical.
Yeah.
Now, formally, I'm not doing a good job because I should be stating the limit as x goes to negative infinity every step of the way, but we still need to go 1 in negative infinity plugged into here, in which case we can do that now. And then negative infinity squared is just, doesn't really matter that it's going to be positive because it's 1 divided by infinity, whether it's positive or negative. That whole value is going to go to 0, right?
Yeah.
And so then you're left with 1 over the square root of 1, which is just 1 on that one. Except the answer is negative 1. And I see why. Error on my part. Why would the answer be -1?
Because of the square root one or because of the negative infinity?
Yeah, so the negative infinity, if you think about it here, if you're plugging in a negative infinity up top here,
Oh.
over a positive infinity, it'll be end up being a -1. Yeah, so that should have been a -1 on top there, so, error on my part not recognizing that. So some of those ones, yeah, I think that's fine for right now. We can take a look at them later. There's a couple trig ones there. We can take a look at 38 just to do a trig one practice. X minus cosine x over x. So x minus cosine x over x, we can still apply the same kind of algebraic process of dividing everything by the largest exponent. So it would just be 1 minus cosine x over x all over 1, that divided by x, that divided by x, that divided by x. And then we know that cosine x over x, as x goes to infinity, when you're plugging in infinity values, if you will, cosine helps us to know the domain of cosine, right? And the domain of cosine is going to be, the range of cosine, what you're getting back out. So you're only going to be getting out between where 1 and -1. So no matter what you're plugging in here, you're only getting out max of a 1 and max, or a minimum of a -1. So 1 divided by infinity, or -1 divided by infinity, that's just going to go to 0 as well. So then you're just left with 1 over 1. So the answer is 1 on that. So, okay, let's stop there. And we'll do a couple more examples Monday, and then that should be pretty good on most of this stuff. We will talk about actually sketching graphs using extreme and intercept symmetry and asymptotes. It's kind of an somewhat extensive process, but going through all the things that you know, finding the extrema and the intercept symmetry asymptotes. We'll do a couple of those.